Hello everybody, welcome to the model validation video of the large-scale machine learning section of MLExpert. Let's say that we have a trained model, and now we want to tune it in terms of its hyperparameters against some validation set. If you need to brush up on this, feel free to view the machine learning crash course. Now, in general, the same techniques that we talked about in terms of training a large model with large data, the same principles can be applied when running inferences against some validation set. However, the main difficulty is finding the best hyperparameters efficiently. Now, with some deep models, it can cost hundreds to thousands of dollars to train these neural networks, just a single iteration. So the idea is that you want to find the best hyperparameters as fast as you can, such that you don't have to repeatedly train the model with new hyperparameters in order to test that against some validation set. Now, some of the largest neural networks can take upwards of $5 million to train just a single iteration. So if we could cut our number of iterations in half when it comes to hyperparameter tuning, we could save a significant amount of money. Alright, so the naive way would be to randomly search through our hyperparameters. So let's say that we had a learning rate hyperparameter, and we could just specify that it has a uniform distribution, and it will be between this number and 0.1. In that case, the algorithm would randomly sample a uniform distribution with these bounds and attempt to find the best hyperparameter in terms of the learning rate that way. Now, the algorithm would sample this uniform distribution with these bounds in order to find the best learning rate. The same would apply for a batch size and maybe a kernel size if we were dealing with a convolutional neural network. However, another way that we could do it is by using a grid search. So in this case, we could list the possibilities that we want to try in terms of the optimal setting for each hyperparameter. So here the learning rate would have these, the batch size would be tried with those values, and the kernel sizing would be tried with those. The reason why grid search may be better than random at times is because it allows us to select intervals that are meaningful. So if we randomly searched, nothing would stop it from testing 0.001 and testing 0.0011. But in this case, it can only test through these values, so we will be guaranteed that we won't test two extremely similar values such that it may not have such an impact when it comes to testing it against the validation set. So grid search and random search are ways that we can typically hyperparameter tune. However, an even better way is to use Bayesian optimization. So here we have a graph. This is the chance of some particular loss given a 50% dropout of some layer in a neural network. This is technically our prior. So since we don't know that a 50% dropout on a given layer would get us some particular loss, we're taking a guess here with our prior, and we're assuming that there is a 0% chance of a zero loss given a 50% dropout. We're also assuming there's a 0% chance, or roughly zero, of a 300 loss given the same 50% dropout. And in general, our prior is saying that it's most likely that we'll get a 150 loss with our 50% dropout. So in the Bayesian optimization case, each of our hyperparameters, here dropout, would get its own distribution. And in general, another dropout, say 60% dropout, would get that same prior distribution. Because again, that's our best guess. We don't actually know if 1% dropout is better than another percent dropout. Again, the same could be true for a 30% dropout. Now, if we take this graph and just rotate it, so here we've just inverted it 90 degrees, so here we still have the percent chance, and here we still have that log loss, and here it's the dropout at 90%. Again, it's going to be the same exact graph, just because we don't know if a 90% dropout is better or worse than a 30% dropout. Now, while still preserving the meaning of this distribution here, let's go ahead and replace this axis with the percent dropout. So here we can actually plot the probability distribution with a 90% dropout rate in terms of its log loss. Again, this is the same thing that we saw before. We've just rotated it by 90 degrees, and we've replaced this axis with the percent of dropout. Let's go ahead and fill in the other percent dropouts that we've had. Again, they're the same exact distributions because we don't know if any one is going to be better than any other. Here what we can do is draw a mean for the peak of the distributions, and these lines would represent the one standard deviation away from the mean, given this exact distribution for all the dropouts. So here we can go ahead and get rid of those distributions because now we're just representing it with these lines for the standard deviation and the mean. And now what we can do is fill in even more of these because, again, they're all the same because we don't know if one is better than the other. And technically, this will be true for every single percent value that is possible for dropout to take on. So what we can do instead of looking at 1,000 of these is we can just draw an outline. So here we're going to have the mean, and these will be the standard deviation. Now, random hyperparameter tuning would go ahead and select a random value of dropout. So here it randomly selected roughly 20%, and that landed the value here after it trained the model with this exact dropout. So here we got a loss of roughly 85. Next, let's say the random sampling chose 80% for the next dropout percentage to choose for the hyperparameter, and let's say that presented a loss of 185. The random sample would continue to pick various points along the percent of dropout probabilities. Now the problem with this random hyperparameter tuning is that it uses no prior information about previous attempts. So let's compare that to Bayesian optimization. Well, here, let's say that we started out with the same exact point. So Bayesian optimization would start by randomly selecting it. So let's say here that we did start with the same value. In this case, since we've now measured that a dropout of about 20% gives us an 85 loss, what we'll do is we'll collapse this distribution to this single point. This is because we have no uncertainty anymore about what that point gave us. So we're now taking our prior, which was this, and changing it to this since we now have updated information. Let's say next, the Bayesian optimization selected this value here. We would then collapse that point. And now remember, last time the random optimization went here, but Bayesian optimization will be a little bit more clever and notice that this area is likely to show more promise than this area over here. So Bayesian optimization would pick some value in this location, and let's say it picked a dropout of roughly 50%, and that resulted in the smallest loss that we've seen so far. And as well, we could update our function. Now, one interesting thing to note is that we got the same answer that the random optimization procedure did, but we got it in one less iteration. Now, if we were to continue this process for every single possible value of dropout, then we would get some result that looks like this. And what's interesting is we've roughly approximated the true function here with something called a surrogate. So this is the surrogate, and this would be the real function that would be generated had we actually run through all the possible values of dropout. So one question now is, how did we actually know mathematically to go in this location? Well, it's actually pretty intuitive. It's called expected improvement, and it represents the probability of some improvement as well as the size of that improvement. So it takes into account the mean of the surrogate that we talked about versus the minimum loss or the best value for the hyperparameter seen so far. Now this algorithm can be adjusted to explore or exploit more. For instance, when we were at this stage of our Bayesian optimization, the random optimization would have chosen this point, and we said that we were going to choose a point in this area because it just looked more promising. So how it actually works is there is a threshold above the best hyperparameter found so far that we were willing to explore around. Now in this example, this threshold is pretty close to the best value found so far. So what does this threshold imply? Well, it means that we're going to have to search in any of these areas because what we want is some expected improvement. So if we were to go right here, we would not expect as big of an improvement as if we were to go here, and that's because this standard deviation is higher than this standard deviation. So with this configuration, we would only be able to explore values outside of this gap here. That's simply because the expected improvement is larger than the given threshold. So in terms of exploring and exploiting, if we were to raise this threshold just a little bit, so let's say that now the threshold is up here, well now we will be going further away from our best known point in order to try and explore more promising options. This is the opposite of choosing a lower threshold, which means we would be exploiting a location closer to the best value so far. Alright, so one negative for Bayesian optimization is that it's not as parallelizable as its counterparts of grid search or random search. This is because we have to have our updated information before we can take appropriate action for the next iteration in the Bayesian optimization process. Now, what are some tools that we can use to help us perform model validation, and more specifically, Bayesian optimization? Well, we can use HyperOpt, and that will work with Spark. We can use AWS SageMaker. That also has grid search, as well as Bayesian optimization. And finally, we can use Google Vizier. Let's go ahead and look at an example of how we can use HyperOpt to tune a logistic regression model. Alright, so here we're going to use HyperOpt on our Spark cluster to hyperparameter tune a logistic regression model in terms of this data here. This may look familiar from previous videos. We just have the interaction counts of each customer. As well, we have a label for whether or not they canceled within a week of the last interaction count day. We have the features and the label columns made up so that we can use it with our logistic regression model. Alright, so here we're using the logistic regression model. We're using the parameter grid builder, and what that's going to do is that's going to do a grid search of all of the parameters that we list in the grid in terms of our logistic regression model. So we can see here that one of our parameters that we want to grid search is the regularization parameter. So here we want it to try two values. We want it to try 0.1 and 0.01. We can see the same thing with the elastic net param. Here, 0 means to use entirely L2 regularization, 1 means to use entirely L1 regularization, and 0.5 here means to use a mix of both. So here we'll only be trying out 3 of those values in terms of elastic net parameters. Finally, we have the threshold and the max iteration parameters as well, and those are also going to be in our grid search. Now, the max iterations, we're only going to try a single value because I only want to use a maximum of 10 iterations. We then pass the parameter grid produced by this builder to the training validation split here. So all this does is it takes in our estimator, which is the logistic regression model, which was produced by the parameter grid builder there. Then we'll use the binary classification evaluator, since this is a binary classification problem. And finally, we'll have a ratio in which we want to use for the training and validation sets. So here, 80% of the data will be used for training, and 20% will be used as a validation set to explore these parameters. Finally, we call fit on this training validation split, and that will begin the grid search of these parameters for this model. Now, after a few minutes, this will finish up, and I've written a little function here to help print out what happened during this grid search. So in total, there were 18 iterations. So for instance, here we can see one iteration had a regularizer of 0.1, an elastic net of 0.5, a threshold of 0.6, and a max iterations of 10. That produced an accuracy of about 73%. If we scroll all the way down, I've written a little note here that we have 18 iterations because there were 18 different ways to arrange those parameters, and we achieved a 76% maximum accuracy. So now what I want to do is showcase how we can use Bayesian optimization to perhaps improve this process. So here from HyperOpt, we're importing several tools here. And then we just split our data frame into training and test. We're going to use the same ratio that we did earlier in terms of the grid search with PySpark. And then what we do is we arrange our search space. This is very similar to the grid parameter search space that we had above, but in this case, we're actually going to specify the distributions that we want each of these parameters to follow, instead of listing the explicit choices that we want the algorithm to explore. So here, the elastic net parameter will have a uniform distribution between 0 and 1. The regularizer and threshold will also be uniform distributions, and they will have their bounds as well. Next, we specify which type of algorithm we want to use for this parameter optimization. So in this case, we're going to use TPE, which is tree of Parson estimators, and that is a Bayesian method similar to the one that we went over. And finally, we use fmin, which means function to minimize, and we give it the function that we want it to minimize. We give it the search space, the algorithm that we want it to use in order to minimize it, and we give it the max number of evaluations we want it to use while trying to minimize the function. Notice here that I've given it half the opportunities to find the best optimization. Earlier, we had 18 iterations, and this time I'm only giving it 9. So what is the function that we actually want to optimize? Well, the train function will take in the parameters provided by hyperopt. So here we get the parameters and we're just extracting them from the map of parameters that is in the argument of the train function. So after we extract all of our parameters that we want to try for this particular iteration, we go ahead and plug them in to our logistic regression model. We call fit on our training data. We then evaluate it against our test set. In this case, this test set is actually a validation set. We've set aside another test set, but in this case, it would be a validation. And here, I'm just going to print the accuracy that we get and the hyperparameters that are specified to achieve that particular accuracy. And this is just what hyperopt expects in terms of optimizing or minimizing some function. So here we're actually returning the negative accuracy because even though we want accuracy to be as high as possible, we're actually returning the negative so that we can minimize it. This status here is just expected. There are cases where you would want to return a status as not being okay, but in our case, we have a very simple model here, and we're just going to return okay when we return the accuracy that we want to maximize, and in this case, minimizing that negative accuracy. So after we run this, it does take some time, just like the grid search, but it actually is faster because we only had to do 9 iterations. And if we go through all the way to the bottom here, we will get the best loss so far after 9 iterations. So we can see that the best loss was negative 0.85, and remember the loss is the negative of the accuracy, so the best accuracy that we got after 9 iterations was 85%. This is a lot better than the 18 iterations that it took to get 75% accuracy with the grid search. Now, if it cost $10,000 each time to train our model, we would have saved roughly $100,000. These savings can be even more dramatic the more expensive your model is to train. So that wraps up the model validation video in the large-scale machine learning section of MLExpert. Thanks for watching, and we'll see you next time.